Good afternoon, everyone. My name is David Fernandez from the WIP lab at Clemson University, and today I'll be presenting our work in progress, detection to explanation, using large language models for adversarial scenario analysis in vehicles. This research addresses a critical gap in current AV security, the ability to not just detect attacks, but also to explain them and to understand them. So let's start with the problem. Current autonomous vehicles heavily rely on deep neural networks for perceptions. However, these DNNs have been found have a fundamental weakness. They're vulnerable to adversarial attacks. Let's look at an example. Let's assume that an attacker can place a simple patch on a speed limit sign. The AV perception module might misclassify it completely. Perhaps instead of seeing what is a 55-mile-per-hour stop sign, it sees a stop sign with a patch. And this has been shown to not be just theoretical. It has been demonstrated in real-world conditions, and it poses a serious safety risk. So traditional cybersecurity approaches to this problem have been focusing on statistic anomalies using classical machine learning. However, these methods have three main issues. First, they struggle with semantic inconsistencies. This means that they cannot understand or make sense of the entire context of the scenario. Second, they require some sort of label training data, which might be difficult to get, especially for novel attacks. And third, they can't distinguish between benign anomalies, like sensor glitches, and malicious ones, like spoof signs. Recent work has shown that LLMs can detect anomalies through human-like behavior, which inspired our approach. So our goal was to create a framework that leveraged LLMs to provide interpretable explanations, meaning it's not just enough to flag that something is wrong. We want to understand why is it wrong. For example, we have the same example, and we want to use LLMs to analyze the scenario with a stop sign on the highway. It could tell the LLM could tell us that this violates the standard traffic regulations because stop signs aren't normally placed on the side of the highway, providing both detection and semantic understanding of the whole scenario. To evaluate our approach, we actually created a dataset called the Autonomous Vehicle Security and Explanation Dataset, or AutoSec-X for short. This dataset consists of 40 structured driving scenarios grounded on the manual MUTCD, which is the Manual on Uniform Traffic Control Devices, which is the main governing element that defines the standard rules for the most common signs in the US. We selected 12 of the most common sections covering the most common traffic control devices. And using GPT-01, we generate both benign scenarios that follow the rules and adversarial scenarios that violate these rules in some sort of way. So the idea is that each scenario is encoded into a domain-specific language. And the reason behind this is because we need the LLMs to evaluate them, and we need a systematic approach. So the DSL allows us to do this. So here's an example of the DSL. Let's take the section 2B05, which specifies where the stop sign should be placed. And a very simple scenario would be that a stop sign appears on a high-speed highway. Our domain-specific language definition could be these elements, but could also include more, like the road type, the vehicle speed, lane markings, if there's a traffic sign, in this case the stop sign, the time of the day, the weather, and a small description of the overall scenario. Our scenario analysis framework works as follows. Once we have the data set in a DSL form, we take the scenarios and pass them through different LLM families. In this case, we use Llama, Gemini, and Shiven. Using a zero-shot chain of thought prompting, we compare their outputs against generally crafted ground truth explanations. And we use two types of metrics, traditional metrics like rouge or blue, or similarity measures as well as SBERT. And we also evaluate via manual review the reasoning behind the decisions of the LLMs. So here's an example of the key differences in two types of model outputs. Our ground truth here identifies the violation at the top and cites specific MUTCD sections that is not being followed. The first thing we noticed is that even smaller models are able to detect inconsistencies. So here, for example, even though Llama were only using an 8 billion model, it was able to detect that there was an inconsistency. However, Gemini models like Flash also produce structured output with clear reasoning about why the stop sign don't belong in highways. It actually also mentions the specific rule that we were looking for. On the other hand, the smaller models produce unstructured output, which meant that we had to manually go into each of the outputs to see if there was an inconsistency or not. And in some cases, it actually generated a hallucination. Here, it generated Python code for some strange reason. So this highlights the importance of model selections because proper prompting only gets you so far. So as far as accuracy and our semantic scores, Gemini models overall achieve the highest accuracy, while smaller models like the 3.2 1 billion model only reach 55%. Interestingly, though, the smaller version of Gemini achieved a higher accuracy than the larger version of it. And there was no accuracy improvement between the 14 billion version of Shiven and the 8 billion version of Llama. When it came to comparing the similarity between the explanation of why it flagged an inconsistency, the larger Gemini models actually showed a closer relationship to the ground truth. This is shown in the overall higher SBERT scores, which show that the Gemini family models maintain a better semantic alignment with our ground truth. The low blue scores on the right, actually, they're super low across all of the models, which this just means that it's just not copying text from the same paragraph. It's actually generating original explanation, which is actually what we want. We also compared the outputs of each of the models between each other, and these correlation matrices reveal interesting patterns. For example, the blue matrix on the left shows that the Gemini models produce highly similar outputs between each other. This suggests consistent reasoning between models of the same family. The matrix on the right shows the SBERT scores. Actually shows larger models have stronger semantic alignment with each other, while smaller models, like the Llama ones that we used, often produce different explanations. This suggests that the model actually impacts in the semantic of their understanding capabilities. So let me summarize our key contributions to our findings. First, we introduced a zero-shot chain of thought approach that enables us to use pre-trained large language models to analyze driving scenarios without any training or labeled anomaly data. This is crucial because it means that the system can detect novel attacks it has never seen before. Second, we create AutoSec-X, a semantically rich dataset of 40 scenarios grounded in actual traffic violations. This is key because unlike existing dataset that just label anomalies, our dataset actually provides regulatory context needed to understand why something is anomalous in certain scenarios. Third, we develop a robust evaluation strategy combining quantitative metrics like SBERT and qualitative with human reviews. Overall, our work bridges the gap between in AV security. We're moving beyond simple detection to actually providing interpretable explanations of why is there an inconsistency in certain scenarios. Moving forward, we plan to expand AutoSec with real-world scenarios from datasets like NewScenes, Waymo, or Kitty 360. We plan to incorporate scenic language to generate visual representations, enabling multimodal analysis using visual language models. And ultimately, we envision this as an anomaly forensic analysis tool that can be used in the future. Thank you for your attention, and I'm happy to answer if you have any questions.